How is everybody? Good. You're just happy to be in linear algebra. I mean, all those other boring classes, and then you finally have a break with the exciting linear algebra class. Anyone get a mission call yet this semester? Anyone get a mission call? Anyone get engaged?
Oh yeah, it's Tuesday, huh?
It is Tuesday. But last week my son got his mission call, and it was on a Wednesday. He found out Wednesday morning that he got the email Wednesday morning. Korea Busan. So anyone here serving Korea? So yeah, he's excited. Well, at least that's where the call is. He'll probably end up half the time in Seattle or something. Who knows? So anyone get engaged this semester yet? Hey, congratulations! So, about 5 years ago, I was teaching a small class of calculus 2, and it was the very first day of class. A few people had trickled in, and this man, boy, whatever, walks in, and he sits next to a girl in the front seat, and he turns to her and says, "Will you marry me?" She said no. He just turned out to be, he had ADHD like no one I've ever seen in my life, and he sure made class fun. He distracted us a lot from mathematics, but boy, he was fun to have in class. Okay. Are we ready to start yet? We are. Who'd like to start us off with a prayer? Thank you. Amen. Thanks. Had a great devotional today. I'd like to, on Tuesdays, try to take a few minutes to talk about devotional, let you guys share any comments that you had. So any insights or things that you enjoyed from the devotional? Anyone watch it? Okay, good. Glad somebody watched it. So anyone have anything to share? Go ahead.
I guess I kind of just like validated some of the decisions I've been making recently. Like some of the things he taught, like I kind of like had in my mind as I was making these decisions, and so like it really affected like the choices I was making, and then just have him explain all of it, like the reasons why, and stuff. It was just so like it was really comforting. Great.
It was a really good devotional. If you did not listen to it, I strongly encourage you to get on when it's up on speeches.byu.edu and listen to it. It was Elder Martino from the 70s. Really good. He talked a lot about agency and not letting Satan can take away your agency or convince you that you don't have a choice in matters. That was one of his big things. That part reminded me a lot of another talk that I strongly encourage you to watch or listen to. It's by Lynn G. Robbins. Elder Lynn G. Robbins, he might be in the presidency of the 70 right now. I can't remember if it's 1B or 2B, but it was an Education Week talk, and it was on responsibility. Exactly. So, oh, you say, am I? I'm sure I'm not, but I'm trying to be. So, but yeah, in there he talks about how there are dual principles like justice and mercy, and agency and responsibility. And Satan tries to separate those and just focus on one, and it distorts the truth, right? He would always just say, you only need mercy, right? God is just merciful. It doesn't matter what you do, he will be merciful. Whereas there's also justice that you need to worry about too. But he talks about the responsibility side of agency, and it is incredible. It's a really, really, really good and insightful talk. I would encourage you, though, that when you read it, or if you're like me, if you're a proud person like me, you're going to listen to it and you're going to start pointing fingers and start to say, like, yeah, that person isn't responsible, that person isn't responsible, that person isn't 100% responsible. Or, if they were more responsible, they would have done this. Please make sure you listen to it and think about yourself, how you can be more responsible. So, okay. And I strongly encourage you to go to the devotionals, you guys. I know you're busy, or listen to them now, wherever you're at. This is one of the best things about being at BYU is having time to listen to those devotionals and forums. So, okay. Oh, homework. So I have the homework written up over here. So from here on out, we're doing something a little bit different. All of the videos, for each section before you come to class, there will be a video. I am going to walk through the annotated slides and make a video of those, okay? So instead of just having you watch the slides, or go study the slides yourself, or instead of just watching the other slides, the other videos we put up, I'm going to make a video. So, and we're going to require you to watch that video, okay? I'll try to keep it short. Hope this first one's less than 20 minutes. So try to keep them 20 to 25 minutes of hitting all the important points. So you can't just study the slides now. Please watch that video. So that's required now. And read 2.3 through Theorem 2.6. Some of the other kids said, we have to read all the way to 2.6? No, there's not even a 2.6. It's Theorem 2.6. So you're reading the first part of 2.3. Then do online 2.3.
I would disagree. Miss Martin's not a very good teacher.
I'm hurt. Okay. Okay, 22B is on the written. Speaking of that, oh, yes. Yeah. Okay. That question was, do you actually read Theorem 2.6? Yes, you can read Theorem 2.6. So once I was teaching a large lecture section of 113, and a student said, I'm confused. And I joked and said, well, I'm doing my job. And another student said, you deserve a raise. Ouch. Okay. All right. Okay, so let's find solutions for this system. Okay, there's a few different ways we could write this system. I could write it as a system of equations. There's two equations here. Each is a plane. Okay. I could think about it as an augmented matrix, right? Take it that, write it as an augmented matrix. I can also think of it as combinations of the columns. What combinations, how much of 4, 2, 1 and the negative 1, 1, 3, how much do I take of each one to get to 0, 2? I can think about it in any of these. Go ahead and start with this augmented matrix and see if you can work through it and get into reduced row echelon form. Okay? Okay? And I'm going to start doing it up here, but please try to do it yourself first. If you get stuck, you can look up. Okay, that's what I got. So just a reminder, there's different ways. You didn't have to follow the exact steps in the same order that I did. There's different ways to get there. But the reduced row echelon form is unique. So as long as we did it right, both did it right, we should end up with the same thing. So, okay. Okay. So I know some of you still might be working. The question I have is, what is the solution to this system? What are the values for x, y, and z that I can plug in and make both of these equations true? Or plug in x, y, and z and get and take this sum and get 0, 2. What are those solutions? There are infinite solutions. Can someone tell me one solution? I'm just going to write these out as a system of equations. Someone find one equation. There's one that's a little bit easier than the others to find.
Like x is 0, y is -1/2, and z is 1/2.
Okay, x is 0. Oh, sorry, x is 0. So you just started plugging in?
Yeah.
What did you, and you started plugging in for x?
Yeah, well, I said x is 0, so then it would be easy to get z.
Okay,
And then I plugged z into the second equation to get y.
okay. So you picked the value, okay? So, nice. Pick the value. Pick a value, and then start solving. Okay? So tell me your solution. It was x equals
X is
0.
Y is -1/2, and z is 1/2.
Z is 1/2. Great. And we could do that again. We could plug in x equals 1, right? So if you're going to pick a value, there's actually a really slick, there's a slick number you should replace. So you can do x, but there's one that's even easier. What value would you pick? Not the value for x. Let's replace a different variable. So instead of picking x equal to something, instead of picking y equal to something, z. Z is a really nice thing to pick a value for. And if you pick z equals 0, that's like the nicest thing. Then you can get x is a third, y is a -4/3, and z is 0. So yeah, 0 is a really nice thing. It saves you a bit of work, right? If you're gonna plug the values in for z rather than x or y. You still might have to do a little work. If you plug in z equals 1, we can plug in z equals 1. We're going to get another solution. You got to take your +2/3, take it over there, take your -5/3, take it over there. Like, we can still get it. But z is a little bit, once we think about it for a little bit, it's the natural thing to start plugging values in for. Okay? In fact, we're going to use that idea to write out all possible solutions for this. So I'm going to write down x equals, I'm going to solve for x. I get 1/3 -2/3 z, and y equals a -4/3 +5/3 z. I have two equations, but I'm missing something. I mean, if you tell me a solution to the system, you need to tell me an x, y, and a z, right? But if we're just picking for z, what's z going to be? It's going to be whatever we pick. I'm just going to write down z temporarily. We're going to come change this in a minute, but Z is going to be whatever we pick for Z to be. Now notice this side. So notice this side. What do I have over there? I have some Z's and I have some constants. Okay? I'm going to rewrite this so it's going to look more familiar to us. Okay, so all I did was I combined all of my Z's. I kind of combined like terms in a vector. So I've got my Z's here, and I've got my consonants. So I don't have a constant down here, so I can think about it as plus 0. So if I take all those, okay, then I wrote down, oh, so I have a negative 2/3, 5/3, and 1 Z, so I can rewrite that as Z times that. And I have a 1/3, a negative 4/3, and a 0. I can write it down like that. Questions on just going from here to there? Okay. How does this represent all of the solutions to this system? How does that represent all the solutions to our system? I can put in any value for Z. I can do the operation, right? I can plug in 27, multiply those out, add there. I get an X, Y, and Z, and it'll make all those things true over there. Okay? Geometrically, what is this? What is this the shape of? Or what object is this? It's not a plane. It's not a sphere. It's not a bird. It's not a plane. Little old me, underdog. I'm just kidding. Okay, it's a line. I have a point. Here I have a point somewhere in R3, somewhere in space. And here I have a vector. Right? Here's a directional vector. Here I have a directional vector, and here I have a scalar of this directional vector. So I've got a point, wherever that is, I've got that, and as I take values, I can multiply that directional vector times anything, any real number, and it will create a, this will point to, starting at that point and going however far along that vector, that directional vector, either direction, any point I can point to there is a solution to that equation, okay, to that system of equations. Okay. Questions about this representing a line? Yes. Yes. So yes, if we have two scalars, then we would have a plane, as long as they're linearly independent vectors. Well, it depends. If the point it turned out to be the origin, then we wouldn't need to write it down. It would just be 0, 0, 0. But usually there is. So there is one weird thing here. This is different than what we've done in the past to write down a vector equation of a line. What's different? What do we usually have here instead of Z? T. Is that what you're going to say? Yeah. We usually put a parameter here. We don't usually put the variable here and here. So we're going to replace that. So instead of starting Z equals Z, I could say I'm going to make Z equals T, And then I can replace those with a -2/3 t, 5/3 t, and write it out that way. One reason why is because, oh, let me just rewrite it this way. This isn't a unique representation. I can take any vector that would, get me in the same directional, that would still lie on that line. And then I could just keep t. If I doubled this, for example, and kept that as z, or tripled it, that would be a nice one, right? If I tripled this, it wouldn't make any sense to have z there, because this entry would be 3. And so then I would have 3z equals z. And that wouldn't make sense. It's not right. So we pull out new parameters instead of z. So what does it mean when you have infinite solutions? One way to think about what's happening is, if I have these 3 packets, and I'm trying to find what combination of these packets will get me 0, 2. Okay? Well, if I have infinite solutions, that means I should have more packets than I need. I only need these first 2 packets. Or maybe these 2. But for sure, we see we actually don't need z, because we could make z 0. We could get rid of that, and we could still get our outcome with just these 2 packets. So I have more information than I actually need to achieve my goal. If we're thinking about this as foods, and we're trying to reach a certain diet, for example, or funds, if these are funds and I'm trying to reach a certain investment goal. Yes? That's right. So here each of these is a plane, and they intersect at a line, and the line that they intersect with is that line. Okay? And in fact, this is, two equations of planes like this, is the general form of a line in R3, in 3 dimensions. You actually just have to write down the 2 planes, the equation of the 2 planes, and the intersection is their line. It's not very simple, right? That tends to be make a little bit more sense, and it's easier to actually find points on that, written the vector way rather than this. Okay? Oh, right. So could you have a unique answer with 2 planes? Nope, you will not. Okay. The 2 planes can be. I brought my Christmas planes. All right. So the planes could be parallel, and then you'll have no solution. They can intersect like this, so they can intersect at one line. They could also be the same plane. So then there's still infinitely many solutions, but you're not restricted to the infinitely many on a line. Anywhere on one plane will be the same point as another plane. So let's talk about how we figure out whether there's infinite solutions. Well, let's talk about no solutions. If you're row reducing, suppose you're row reducing and you get this. Last time I wrote a 6 right here, and it wasn't as nice as that 6, but the student thought it was another 0, and so let me change it. If you end up with all zeros over here and a 7 over here, or some non-zero constant, there's a problem. What's wrong with that?
Nothing equals something.
If 0x plus 0y plus 0z equals 7. But this whole side, if you have zeros of all those, there's 0. Does 0 ever equal 7? Only if it's a really large 0. I'm just kidding. No, it doesn't work. Okay, so this is your sign that you have no solution. It's inconsistent. if you end up with all zeros, we'll do a case like this in a minute, but if you end up with all zeros, you still don't know. There still could be finite or there could be infinite. You're still not sure. That's not what determines. What determines is whether we have a free variable or not. So notice here, we've got two pivot columns. We've got two pivot columns. This is not a pivot column. This means this is a free variable. Okay. If we have three total variables. We have two, they're called two leading variables, okay, with the pivot columns, and one free. Okay. The number of variables will always break down into a number of leading variables and free variables. We call this the rank theorem because the number of leading variables is called the rank of your matrix. Okay, so the rank of the matrix. Yes? Yeah, so the number of, we could say this, two leading variables, we could say two pivot columns, say two pivot positions. Yep, all of those are the same. So, yeah, so two pivot columns plus one free variable. Nope. Just getting into row echelon form is enough to know where your pivot columns are. And so, yeah, you don't have to get into row reduced. So, into reduced row echelon form. You usually have to do some work, though, to it to figure out where your pivot columns are and how many you have. Yes?
So on that one over there that has all zeros, is the rank of that one 1?
The rank of this one would be 1. So you just have one. You just have one pivot column. So this isn't in row reduced, I should move the zeros over. 5, 3, 0. Oh, nope, I shouldn't do that, never mind. You can't do that. Well, I mean, you can, you just have to keep in your mind you have X, Y, Z's. So, yeah, we probably should move the zeros over. Right, if you're writing down the equations, it's just the same as moving your Y's over here. Your Y's over here and your X's over there. So.
The textbook says the rank is the number of non-zero rows.
Right. Yeah, which is the same because the number for every row in row echelon where you have a leading entry, you can turn the rest into zeros. So yeah, so all of those things are the same. So like the number 2 non-zero rows in row echelon form plus your free variables. So yeah, I mean it's like all those things turn out to be the same. So that's one of the hard things about this part of this class. We just find out 100 different ways to say the same thing. So. Yep. So, yep, that means you've got infinite many solutions. And that usually means it's, on a line, like any, it doesn't mean that you can just throw in anything for X, Y, and Z and it works out. It's any point on a line or on a plane or hyperplane. Here, let's do a bigger example. I'm going to write down a matrix in reduced row echelon form, and I want you guys to write down the solutions. Okay, so work on writing down the solution set for that system. Oh, yeah, great. Let's just use, we'll just number them x1, x2, x3, x4, and x5. Okay. So in the last class I used x, y, z, w, and u, but you can see why mathematicians like to just start numbering the variables. So our solution set will be something like this. Each of those variables equals what? So, and of course you could choose, like we would just be naming them different things, but in the end, if we both did it the same, we could just, I could rename mine like yours, and or you could rename yours like mine. I turned it off, sorry, when I was walking around. Okay. I accidentally went with this mic when I went to the bathroom in between. Luckily, I had it off. But, you know, next time I'll be sure to take it off. But could have been really embarrassing. All right. Yeah, I have three pivot columns, so I know the rank is 3. Any of those ways helps me know the rank is 3. So how many free variables do I have? 2. Because the number, I have 5 total variables, and they have to be split up amongst the ones where I have pivots and the ones where I don't. The ones where I have pivots are called the leading ones. but I have two where I don't have pivots. So these two have to be free. So x3 and x4 are free variables. Okay? So they're going to be my free variables. So to start off with, I saw a lot of you doing this. Let's write down the equations. So I was really comfortable with the much more comfortable with equations when I was in your shoes than I was with matrices. So I'd get to this point and I'd be like, I'm going to write down the equation, figure out what I have going for me. So x1 plus x3 equals a minus 5. x2 plus 2x3 minus 2x4 equals, get that right, negative 4. And x5 equals a negative 2. I never was very good with numbers. Yeah, that's why I used letters. Okay. All right, so I can solve for x1, I can solve for x2, I can solve for x5, right? Where are my free variables? I've got some, they're showing up here, but I want to have an x3 equals and an x4 equals. What am I going to let x3 equal? Yeah, so I could let it equal x3, I could let x4 equal x4 while I build up my vectors, or I could call one t and one s and go replace those up here. Okay? Let's do it this way where I call one t and one s. Okay? So I'm going to say this is t, this is s. So I'm going to rewrite these. x1 plus t equals a minus 5. x2 plus x3 is t, so plus 2t minus 2s equals a minus 4. And I'm going to change the order here so I can keep my x1, x2, x3, x4, x5. And I'd like to have this x5 down here. So I'm going to put x3 next. So x3 equals t, x4 equals s, and x5 equals a negative 3. And now I'm going to start solving. I'm going to solve up here for x1, solve this one for x2. So x1 equals t minus 5, x2 equals a negative 2t plus 2s. I'm going to move that 5 over. x3 equals t. Oops, did I miss some? Oh, minus 4. Thanks. And then x4 equals s. I'm lining up my similar terms. Yep. Thanks. If you don't like it being positive, we'll make it a negative t. Should have a positive attitude. Some people just don't like that. Just kidding. Okay. So now I've solved for x1, x2, x3, x4, and x5. Okay. And I've tried to line up my t's, lined up my s's, lined up my constants. And now we're just one step away from writing this down in vector form. I'm going to take all my t's, write it as t times a vector. I'm going to take all my s's here, write it as s times a vector, plus my constants. So what's that going to look like? So t times, I have a minus 1, a -2, 1, 0, 0. S times 0, 2, 0, 1, 0. What's up with my zeros and sixes today? Just kidding. Thanks. Oh, this one too? There, is that better? Okay. And then -5, -4, 0, 0, -3. Okay. All right. So now I have a point. This point is a solution. If T and S are both 0, then that point is a solution. Right? In fact, this gives me a way to generate all, or a whole bunch of solutions. I pick any value for T, any value for S, multiply T times that vector, S times this vector, add it to that point, I've got a solution.
The number of free variables plus 1 is the number of terms you're going to have in your solution.
Possibly, if these end up being linear combination, if this is a scalar multiple of this, you could actually end up with just back to a line too. So, yeah. So this is a plane. Yep, this is a plane. So I start with a point, and then I have 2 direction vectors, and I can go as far as I want. I hurt my shoulder last night, so it's hard for me to do some actions. I can go as far as I want this way, and as far as I want in this direction, and get to any point in that plane. I can go negative. I can go negative. So, yep.
So, if S was a scalar multiple of T, then is there a chance that we can get to this point without having to figure that out yet?
I don't know. Yeah. I don't know. We haven't bumped into any of those, and those are trickier matrices we usually bump into later. So actually, don't know. If I had taught this course before, then I'd know. But you guys are my guinea pigs. Well, actually, the first course is my guinea. You know, the 1 o'clock class is my guinea pigs. You guys, at least, I can correct my mistakes from there. So, all right. Right. Yeah, we have the 2 parameters. Yeah, we have the 2 parameters, and yeah, so we can span 2 dimensions. So, yes.
Isn't an intersection of 5-dimensional hyperplane?
Yep. Well, yeah, you have three hyperplanes. So yeah, they intersect in a single plane. So hard to visualize.
So what's the point of like those? Like you need those. If you didn't have the zeros in the bottom, would still be the same answer.
Right. Like if they just gave you this system, then it would be the same answer as it. Like presumably we started with five different equations and we reduced it, and those ended up at 0 later on, right? We didn't just add those zeros just for fun. But all of that information in those 5 system, in those five equations, is just captured in these 3 equations. So, yeah.
So when it gets to that point, it's considered R5, like a plane is R5, or?
Yep. Yeah, it would be a plane in, or a hyperplane in R5. So no, a plane in R5, yeah.
So is this solution we found also a solution to something in R3? If you only look at x1, x2, x3, because over there, if it's all zeros, you have to.
I guess it could be the solution to R3 if it was like the same.
If you fix x3 and x4 to be 0, then you're basically reducing it down to an R3 case. So that would be what we might call a shadow of the hyperplane into 3-dimensional space. But
So those 0 rows don't get rid of any dimension.
That's right, there's still 5 variables, so don't let those throw you off. But if we had started with the five equations and simplified it down to this, we actually, all the information we could capture in just 3 equations with the 5 variables. Yep. Okay. Yeah, one point about just because you might have infinite solutions and you might have a row of zeros like that, but just because you have a row of zeros doesn't mean you have infinite solutions. If we simplify, if I take a -1, 1, a -1, a -1, 2, 2, augment it with 3, a -8, and a -12. If I row reduce this, I get down to 1, 0, 0, 0, 1, 0, 2, -5, 0. So that's not a 6. Okay. Neither is that other one that looks like a 6. Okay. Maybe you should start doing like that. Yeah. Okay. I still have 0, 0, 0. Okay. Well, in this class, phi equals 0. Okay. Always. No. So I still have this 0, 0, 0, but in the system, I know that x has to equal 2 and y equals a -5, and I only have 2 variables. Like if I wrote down the 3 equations, I've still just got x's and y's, and I know x has to equal 2, y has to equal a -5. And what's happening here is I have these 2 lines, I have these 2 vectors in 3-dimensional space. They span, combinations of them span a plane, and this point happens to be in that plane. And there's only one way I can get there with the combination of those, and that is taking 2 of the first column and -5 of the second column. But if I happened to change one of these numbers and make this -11, then my 0 here would be like a -1 or something. And now I'm not in that plane. This point is no longer in the plane spanned by those two vectors. And so now I have infinite, now there is no solution. No matter what combination I take of these things, I could never equal that. So that's one way to make sense of what's going on. All right, have a great day. You're welcome. Thanks for all your questions, you guys.
you're free.